morning, everybody. This research is, it actually starts from the analysis of a case study. And what I'll try to do is to provide some ideas. This section is called wider thinking, some general ideas on how to design a more sustainable tall building from a life cycle perspective. I would like to thank Anthony Wood because this morning he showed exactly the same picture of Miss Van der Rohe's Seagram building, referring to it as the commonly developer building. I mean, something that developers like a lot in terms of efficiency, in terms of simple extrusion of a very efficient floor plan, and so on. And I would like to start this presentation by reading with you one of the strongest comments that I have read on Miss Van der Rohe's architecture and on the architecture that has been inspired by the work of Miss Van der Rohe. And this definition is provided by Peter Buchanan, who's a critic of architecture, of course, at the Harvard Design magazine. In retrospect, the post-Miesian tower, all those towers that have been designed according to this masterpiece of architecture, the monofunctional rectilineal vertical extrusions, clad in dark or mirrored glass, marks architecture's all-time nadir, which means the lowest part, the lowest point of architecture in all the time. Such towers were efficient in the narrowest sense, maximizing the ratio of net lettable to gross floor area and minimizing the area of external envelope in relation to lettable floor, so very efficient towers. The quickness of their construction minimized building and interest costs, but ignored long-term running costs, including those of energy consumption. This is a very strong critique, and I think that most of us would agree on the negative impact that those towers have on the energy consumption and on the sustainability of the tall buildings. As I mentioned to you before, this presentation starts from the analysis of a case study of a very sustainable tall building. It is the Palazzo Lombardia building, just finished in Milan. This building received, actually we received next November in Chicago, next October in Chicago, the CTBUH Best Tall Building Award for the European section. Strangely enough, it's a public building. It's not an office building, it's not a residential building, but it's the siège of the regional administration of the Lombardia region in Italy. Lombardia is one of the richest regions in Italy. A public building means that I can go there anytime I want. It has a height of 160 meters. It's not a very tall building, but it was the tallest building in Italy when it was completed. And it was designed by Pay & Cobb and built by Impregilo. This building represents, according to many, one of the state-of-the-art in sustainable design of tall building. And it has all the devices and all the design principles that we commonly refer to as sustainable design of a tower. As we can see in this picture, it has a photovoltaic system on the southwest facade that can provide 10% of the electricity consumption within the building. It has a very efficient curtain walling system. It's called the climatic wall, and it attains an important value, a U value of 1.1, which is a very efficient curtain wall facade. It is composed by a very deep, it's almost a meter thick double glass curtain wall. It has chilled beams, but not just this. It has also a lot of other ingredients of what we normally refer to as sustainable tower. It has green roofs with local plants. It uses local stone for the not translucent double skin facades. It has heat exchangers that use around 40 deep wells to exchange heat with the deep water under Milan, which has an ideal temperature of 15 degrees, which makes it very efficient both in the summer for cooling and in the winter to preheat the hire that will be needed. And it has a LED lighting system. These are non-official figures because the building is, as it has just been completed and it is now fully occupied, it is going through a tuning process that will try to maximize the efficiency of all these devices. So these are non-official figures that I found in the press or with talks with the designers and the engineers that worked on the project. It has a very efficient heating and cooling energy consumption. It is supposed to achieve an A level certification in Italy, which means under 30 kilowatt hours per square unit in a year in terms of external primary energy, plus of course the energy that is provided by the sustainable devices that we saw. And it has also very efficient internal equipments that consume between 60 and 70 kilowatt hours per square meter. So this actually allows Palazzo Lombardia to reach the maximum levels of efficiency in terms of energy consumption. Mahadevra Dam in 2001 created sort of a scale of the maximum efficiency of tall buildings, and it identified a boundary level between 80 and 90 kilowatt hours of total energy consumption as the maximum achievable efficiency. And of course, we have a very poorly designed towers, those before the energy crisis, in particularly harsh climate, which means both very cold cities like Toronto or Moscow, or very hot cities like Houston or Dubai or many other cities in the world. Then we have other generations of tall buildings, and the very straight line is between those that have been built before the 1974 energy crisis and those that have been built after this period. And so Palazzo Lombardia almost reaches the boundary level. But when we talk about LCA, life cycle analysis, energy analysis, we should refer also to what is also called gray energy. And this is the embodied energy. We have seen a lot of speeches this day about this topic, embodied energy or embodied carbon. And it is commonly defined as the energy that is required to produce, transport, and install the materials a tall building or a structure is made of. There are several methodologies. This is a very tough problem to the quantification of embodied energy, because we cannot read the embodied energy consumption as we can do with gas or electricity, but we have to calculate it. And there are mainly two different methodology. One is the International Standard Organization compliant methodology, which means trying to analyze all the production phases of a material or of a building product and identify the energy inputs that were required for this production. And the other one is, it was suggested by Vasily Leontiev and is based on the input-output tables of economics exchanges within the industry field of a country economy. Then there are some hybrid methodologies. The most defined one was proposed by Treloar. He was a researcher at the Deakin University in Australia. And it is a combination of these two accounting methodology. It uses the tables that can commonly be found on the internet for the 9 most important materials within a construction, most important in terms of quantity. and it uses the generic input-output economic tables for all the other methodologies. I don't want to bother you with the details of the benefits and the pros and the cons of the two methodologies. There is quite a lot of literature on the topic. But this is just the methodology that we used for the calculation of the embodied energy of Palazzo Lombardia. So we identified those that are considered to be the 9 most important materials present in the building. So concrete, of course, but rebars, glass, aluminium for the facades, and also the carpet used for the floors. And we use the tables that you can really easily find Googling embodied energy of building materials on the internet. And we identified an amount of embodied energy for those 9 materials. The rest of the building, the embodied energy of the rest of the building was calculated using the real building prices that were paid for building the Palazzo Lombardia building and using the input-output tables. This is a much more complex methodology, but it's also more refined somehow. Anyway, we achieved a level of 718 millions of megajoule, which is just a number in terms of energy. So an interesting thing to do is to try to do a life cycle energy analysis and to compare the embodied energy of the building and the annual consumption of the building. And the result of this analysis is that the returning time, it means the time that the energy consumption, the annual energy consumption needs to equal the embodied energy of the building, is 68 years. But these figures also include those aspects that are not really pertaining to the tall building design, like the use of computers or the electricity needs for heating the water, or all those other aspects that are not really bound to the design of a tall building. We are designers, we are architects, we are engineers, we are mechanical consultants, so we design the tall building. We can design the computer that the tenants will use, or the other facilities, the laundry machines that those who will occupy the building will use. So we can just focus on this. If we just include the energy consumption needed for heating and cooling the building, we reach an astonishing level of 150 years, 146 years, which means that embodied energy, the energy that was needed to create the concrete, to pour it, and to transport it into the building, equals almost 150 years of the energy consumption of the building. This is a lot. This is really a lot. Because it's an energy efficient building, so these figures, the annual energy consumption and the total energy consumption, are quite low. In less efficient building, of course, this figure is very different. It can be 15 years, it can be 20 years, it can be 50 years. But when we talk about sustainable tall buildings, very efficient tall building, this is the numbers that we receive. So what we try to assess were some alternative design of this building. What if this building was designed not using a concrete structure? It has a very simple concrete core and concrete columns structure. What if it was designed using a metal frame structure? We found some data in the literature, mainly by Kyung-Sun Moon, who is attending this conference, for a similar building. Approximately the same height and the same floor plan. Of course, it has a different shape that might affect, for sure, the average number, but this is just a very general, a very wide thing about how you can design a tall building. So if you modify the vertical structures of the element, and I use the figures that Kyung-Sun Moon provides in his paper, you slightly modify the energy, the embodied energy of the building. It's a very, very small change in the total figure, 4 or 5% less in this case. But the important thing is that the structural system don't affect, or almost doesn't affect at all, the energy consumption of the tower. So in order to identify the most suitable design solution, I try to modify also something that has a much stronger impact on the energy consumption of the tower. And this is, for instance, the glazing of the building and the double skin that this particular building uses. So what I tried to do was to change this super efficient climatic wall with a norm-complying 2.2 U value standard double skin facade and a very inefficient pre-energy crisis glazing. And the results are that, of course, the pre-energy crisis facade attains a very poor, a very inefficient, creates a very inefficient building. But actually, a standard design facade have almost the same impact from a life cycle perspective on a 30 years life cycle. But if we extend the life cycle of the building to 50 years, we have to imagine that the curtain wall will be renovated. So we'll have to add additional energy to the curtain wall system. And so on a 50 years life cycle, this figure is approximately the same. It's actually lower than this building. Can you still hear me? Yeah. So what we try to do is, you can find other simulation in the other calculation that we did in the paper. But what we tried to do was actually to identify some strategy for a more efficient energy design of the building. This is not an error. All tall buildings start from an empty page, an empty piece of paper, or an empty monitor screen. So everything that we design comes from this. So the architect's and the engineer's responsibility on the embodied energy of the building is crucial. While you design your tall building, from the very early sketches, you define the sustainability from a life cycle perspective of that building. Again, if you just Google sustainable tall building, this is one of the first answers that you receive in Google Images. And I want to compare this building to that one, the classic, highly speculative tall building. It's the architect's and the designer's choice if you want to have this or that. Of course, also the client and the tenants will have their impact, but it's mainly on the architects. Embodied energy, again, just a couple of figures. To produce 1 kilogram of concrete, you will waste the same amount of energy than 2 hours of operation of a standard domestic air conditioning unit. If you wanted to produce a kilogram of steel, you use 11 hours, kilograms, not tons. The building that we just saw had 300 millions of kilos of concrete. So this is the most efficient design for the structural system of a tall building. I'm talking about the structural system especially because it affects the shape of the building and it is the largest amount of building materials that we saw. So this is the most efficient design, the simplest design, just vertical columns that load the bearing, that bears the load of the building and transfer it to the foundations. This is a very interesting building. It's Renzo Piano design for the Intesa San Paolo building. It's under construction in Turin, Italy. He wanted a cinema under the building. I'm not complaining about Renzo Piano for sure. I'm not in the position of doing so. But no one asked for a cinema under the building. And this design solution to have the cinema under the building and not near the building or on top of the building required the construction of this incredibly large transfer beam. This weighs 2,400 tons. It doesn't matter how efficient your tall building will be in terms of energy consumption. You will never, ever pay back the energy that you spent on this beam. not even in a 1,000-year lifespan. We have very long cantilevers. We actually have a swimming pool up here. And the amount of steel that is needed to have the swimming pool is enormous. And this is an architect's choice. This is the designer's choice. We have tilting building. This half of the building actually weighs double of this because it has to avoid the building to bend over because of this tilting element. And that's the architect's choice. Actually, this is a double mistake because there is exactly the similar building, specular, on the other side of the street. And I just want to complain with the architects. I'm an architect, so I can do this. I also want to complain with the structural engineers because you guys have to say, no, this is unsustainable. We cannot build this. And if you don't warn me, that's a problem. Choice of materials. You can unbuild a steel building, but you have to demolish a concrete building. So steel is more expensive than concrete. Concrete has some advantages from many points of view. But if you're building a highly speculative building, build it in steel. In 50 years, when you will demolish your building, you can recycle the steel. You cannot recycle the concrete. You can just crash it. Again, facades. The guys from Permastelisa this morning showed us a very thin curtain walling system that is very efficient. These guys wanted to have this building, and this building, let's say a given amount of net rentable area. But they decided to build a very large, a very thick facade. And they had to add 3 or 4 extra floors for the building. Because of course, if you have a very thick facade, you lose lettable area. So they needed this extra floor. Elevators. There are different schemes to arrange an elevator in the building, and the sustainability of an elevator system is not in the energy consumption of the cabin. It's in the number of the elevators. If you can convince your tenant or your, those who will occupy the building, that having to change in a sky lobby is not such a big deal because they can enjoy the view, they can have a coffee, they can meet colleagues, and they will save not only money because this extra elevator takes out a lot of, costs a lot of money in lettable area, but also they can save building materials. This is where you can actually have a voice in the sustainability of a tall building. Service core. The ventilation system here, the natural ventilation system here in the Swiss Air Tower is actually part of the service core. It's a natural system, but it can actually be a void, an internal void. So if this was more compact in terms of floor plan, that would have been much more sustainable than with the voids, because it doesn't need any material to build the part of the building that you're actually not building. And when the students ask me, what is the most sustainable part of a tall building? I reply, the most sustainable part of a tall building is the part that you don't build. That's crucial. So keeping all this in mind, I would like to read again this sentence, this very hard critique, without mentioning some of the parts. In retrospect, the post-Miesian tower, the monofunctional rectilinear vertical extrusion, was efficient in the narrowest sense, maximizing the ratio of the net lettable to gross floor area and minimizing the area of the external envelope in relation to lettable floor. Are such towers so bad? Are they so unsustainable, like people continue to say? They save a lot of energy in building materials. Maybe they spend a little bit extra energy in daily consumption, but they save hundreds of years of energy consumption through a very efficient design of the tower. Thank you very much.